This is the 4.1 to 4.2 review. Calculators are allowed, and it's number 8. The question on 8 is, how many numbers in the given interval satisfy the conclusion for the mean value theorem for each of the following? So, we need to know what the conclusion of the mean value theorem is before we can answer the question. So the conclusion of the mean value theorem is f prime of c equals f of b minus f of a over b minus a for some c in the open interval from a to b. So if we look at part A, we can see that our a is a -3 and our b is a 4. We can also see the derivative will be the first times the derivative of the second plus the second times the derivative of the first. Our goal is to find out when f prime of c, which is this thing with c's plugged in, when that equals the secant slope. So the secant slope will be f of 4 minus f of -3 over a 4 minus a -3. So looking at this right now and realizing that I have calculators allowed, I'm going to follow some calculator computation steps so that I don't end up wasting a lot of time. Because this is a multiple choice problem, I want to be able to just count. Since I want to know how many numbers are occurring, I'm going to use my calculator and the graphs of the derivative and the secant slope and then simply count the intersections. So what I'm going to do to help automate the process for me, let me move this light a little closer maybe, is, sorry, I wish this were brighter. Let's do this. That's a little brighter. So I'll clear out what's in there. And I'm going to start by going to my y equals. And I'm going to put my original function in y equals, which is x squared minus 8 times x squared plus 6. The reason I'm putting the original function in there, the reason I'm putting my original function in there is because I want to be able to evaluate that function at my a value and my b value without having to plug stuff in by hand. In y2, I'm going to put my derivative. So my derivative, if you recall, was 2x times the x squared minus 8. And I will add the x squared plus 6 times the 2x. So here we've got my original function, then we've got my derivative function. So on the home screen now, I'm going to figure out what that secant slope is. So the secant slope was the original function, which I put in y1, at b, which is 4, minus the original function evaluated at a, which was -3, and then I'm going to divide by, open the parenthesis for the bottom, the b minus the a. When I hit diamond enter, I can see that my secant slope is 23. So I want that 23 to be in my picture when I'm counting intersections. So I'll go back to y equals, and I'm going to put 23 in here for y3. Now my goal is to count how many times the derivative equals that secant slope. So when I graph, I don't want to see the original function. So I will turn it off by arrowing up to y1 and looking at f4, which has that little check mark on it. So if I type f4, it turns off y1. So now I have my derivative function and I have my secant slope. I want to know how many times they are equal to each other in the open interval from A to B. So that gives me window information. My window needs to be from left to right, A to B. So that will be my x min and my x max. Now I need to see when this function crosses the 23. So that means vertically I need to be able to see 23. So for my y min and my y max, I need to make sure that that's somewhere in the middle so that I can see it. So I'm going to go to my window and I'm going to set my x min to -3, which is my a value. I'm going to set my x max to my b value, which is 4. I'm going to ignore the scale. I don't really care what the scale is. Then I'm going to go to y min, and I need to be able to see 23. So -10 is below 23, and I could probably go up to, say, 30. Now you can pick any two numbers that are going to flank 23. You just want to make sure that you don't go so far up and so far down that you can't tell the difference between 23 and the x-axis. So as long as you can see space between the x-axis and 23, your window will be good. So now that we have our window set and we have the correct functions checked to be graphed, we will do a second graph. Here comes my derivative function. And here comes my 23 representing my secant slope. And we can see that in that interval, from -3 to +4, I only have one value of c that works. So back on my paper here, there is only one c that satisfies. Notice I don't have to find out what it is, I just have to find how many there are. So let's do the same process with part B. With part B, my function is x squared times the sine of x. My derivative function will be the product rule applied, which is the first one times the derivative of the second plus the second times the derivative of the first. And we can see that a is -pi in this problem and b is 2pi in this problem. So before I go put anything in the calculator, we're going to graph y1 to be f of x, or enter y1, excuse me, y2 to be the derivative, and then we're going to use a window that has x values from -pi to +2pi. We'll figure out the y range once we figure out our secant slope. So the secant slope will be that f of 2pi minus f of -pi over a 2pi minus a -pi. So let's go to our calculators now and put that information in. We will clear out what's in there. On the home screen, we'll clear out and go back to our y editor. y1, remember, is your original curve, x squared times the sine of x. y2 is the derivative, which is x squared times the cosine of x plus the sine of x times 2x. Then on the home screen, we're going to figure out what that secant slope is. So that's the output of the original function. So we're going to make a fraction that is the secant slope. So we'll have y1 of a, which is, or excuse me, b, which is 2pi, minus y1 of a, which is -pi, close the top, divided by the bottom, which is going to be 2pi minus a -pi. Close the parenthesis, hit diamond enter, and we see that our secant slope is 0. So in y equals, we'd want to plot 0 in y3. Notice that we only want the slope to equal the slope. So tangent slope to equal the secant slope, that means we don't want to graph y1. So arrow up to y1 and turn it off using F4. Now we need a window that we can see both 0 and our a to b. So in the window, my a, if you remember, was -pi. My b is 2pi. And I need to be able to see 0. Well, going from -10 to 10 would definitely show me the 0. So we'll just use -10 to 10 and graph. Remember, we're counting how many times that derivative equals the 0. So we can see it happens 1, 2, 3, 4 times.